wait, I'm not ready.
So, first question. You talked about this, or you did this yesterday. What's a sampling distribution model?
Collection of all the possible samples.
Speak louder, Pam.
Did you say that louder, Steve?
A collection of all the possible samples you could obtain.
Okay, so it's a collection of all the possible random samples. From what? Where do you get a sample from?
Population.
Yeah, from the population. So, yesterday when you got a sample of 5 movies, and then you repeated it, and everybody got 4 samples, was that a sampling distribution model?
Just a mic.
It's just a model. Why was it not a sampling distribution model?
Because there's no way we can reflect all the
Right, we didn't get all possible random samples. We got a few, 4 each, so about, I don't know, 50. But that wasn't all possible random samples. So can you ever actually find all the possible random samples? We've done this before. We talked about this. What?
It'd be really hard.
It'd be really hard. So that's what the word model even means. It's theoretical. You can't ever really do it. So it's just what we imagine that it would look like if you could get all possible random samples. So we are going to think about, I'm going to show you something that you might find useful or not, and we're going to look at it anyway. And see what happens when, this is the population, when the population is skewed left, or the population is symmetric, or if it's skewed right, what happens to the sampling distribution model? So you can just watch. Okay, so this up here is the population. What is that right now? What's the shape? Skewed left or skewed right? Skewed left. Okay, so this is what you did yesterday. You got 5 movies and then found the average. So this is called a simulation. It gets 5. It picks 5 things out of the population and then finds the average. And if we kept doing that forever, that would be called a sampling distribution model. So I'm going to keep doing this to infinity. And someday you're going to see what it looks like.
Wow.
Okay, so anyone want to take a guess? Every time it's finding the average, what happens when you find the average of anything? Like if you're in a class, you make a A on one paper, you make a B on a paper, a C, 2 D's, and an F. What's going to happen? What are you going to get with the average? Is the average going to be an A?
No.
No. What happens? Kind of goes towards the middle, right? So that's exactly what's happening. Even when it gets a few from the sides, the average kind of ends up somewhere towards the middle. Okay, so if you kept doing this, there's 2,000. Okay, so this would be the sampling distribution model. What is the shape of that model? Yeah, is it better than this one? Yeah, it's now unimodal, but it's still a little bit skewed left. So when you have small samples, that was a sample of 5 like you did yesterday, if the population skewed left, then the sample redistribution is also skewed left. This is like going to totally confuse you, right? If the population skewed left, the sampling distribution model is skewed left. Are you surprised by that?
No.
Okay, so that was with a small, I don't do this for every single one, but that was with a small sample size. It says n equals 5 here. So what if we use really big sample size? So if yesterday, instead of having to get 5 movies, if I'd had to get 25 movies for every sample. If you find a big one or a small one, what's your average going to end up being?
More towards the middle.
More towards the middle, because you're going to find the average. So if you got, so if you got 25 from the population, okay, you guys need to pay attention, put other stuff away. This may seem easy, but it is really important. So that's like if you pick out 25 and then find the average. And we kept doing that over and over. To infinity. Now look at that. What's the shape?
Fairly symmetrical.
Yeah, very symmetric. If I kept doing. And now the computer's stuck because it needs to find 7,000 more samples. Oh, it's close enough. Is this normal? We're pretty close. Is it unimodal and symmetric? It may have killed the computer. Oh well. Okay. So if you get really large samples, now it's going to be approximately normal. That's surprising. Maybe, maybe not. It's actually a really big deal. It's saying no matter what your original population looked like, if you get a sampling distribution model, that means you get a whole bunch of samples, eventually it's going to look like the normal model. Even if the original population could be bimodal, it could be very, very skewed. Okay, so the same thing would work, I won't show you again, but for skewed right. So if you have a small sample size, what do you think the sampling distribution model is going to look like? Skewed right. But if you have large samples, it's going to be you see this? That's bad. Okay, so the last one. So let's say the original population is symmetric. That hardly ever happens. But if it was, and you did the same thing, you can even have small sample sizes. And you pick 5, and then you find the average. You pick 5 more, and then you find the average. And you keep doing that. If the original population was symmetric, what does the sampling distribution model look like? Yeah. That's probably not quite as maybe all this is easy. And so obviously if you have bigger sample sizes, it would also. Okay. All that together is what's called the central limit theorem. So you can read that if you want, but it basically says what we just talked about. It's saying as long as you have large sample sizes, and large for us is usually bigger than 25, bigger than 30, then the sampling distribution model will be normal no matter what the original population was. But that only works for large sample sizes. Okay? It doesn't seem like a big deal, but that's why we can do all the hypothesis tests, all the confidence intervals, everything's based off the normal model. Questions so far? Okay. This is on your paper. So the sampling distribution model for means, like I said, I put this back up here because we had formulas for proportions. Remember we said a sampling distribution model is normal, and then there was a way to find the mean and standard deviation. We're going to do the exact same thing, but now we have a new formula for mean, a new formula for standard deviation. The only thing that's going to be tricky, it uses the word mean a lot. The way you read this is that's mean, yeah, it's the mean of all the sample means, or the mean of the sampling distribution model for means. Okay, because what's an X bar? That's average or mean of a sample. Mu is average or mean of a population. When you put them together, it's the mean of the sampling distribution model for means, or the mean of all the means. So this is the formula for the mean, this is the formula for the standard deviation, and I did use the wrong one yesterday. I forgot to do the radical, but okay, here we go. So let's get to the problems. Now you actually need to try something. Ready? Okay, so it gives psychologist data about the incoming freshmen indicates that the mean of their high school GPAs was 3.4. That's a smart. That's all the incoming freshmen. Yeah, with a standard deviation of 0.35. The distribution is roughly normal, and it says the students are randomly assigned to freshman writing seminars in groups of 25. Okay, so it says the mean of all their high school GPAs was 3.4. So that is from the population or from the sample? Population, yeah, it's all the incoming freshmen. Okay, so the population mean You have to get in the habit of using the right symbols. That's the population mean, where their GPA was 3.4. And the population standard deviation was 0.35. Okay, so now it says what's the mean and standard deviation of this sampling distribution? Okay, so all you do is use the formulas. So the mean of all the means is 3.4. That's one of those super complicated formulas. And then the standard deviation of the sample means, so that one is not 0.35. Use this formula, so it's 0.35 divided by radical n. N is the sample size, so what's n? 0.35 divided by radical n. Yeah, 0.07.
Yeah.
Exactly 0.07. That's
Exactly.
exactly 0.07.
I got it.
No, it's 0.3.
I also. Okay. This is easy, right? Now this part should be reviewed. Draw and label the sampling distribution model. Let's go fast. I don't want to waste time doing this. Right, mean goes in the middle. So 3 standard deviations to the right, 3 to the left, and add the standard deviation as you go to the right, subtract as you go to the left. 3.47, what's next? 3.54? 3 something. 61. You tell me what's to the left, 3.4. 3.33, 3.26, and 3.68, 95%, 99.7. I didn't write it down. 96. Oh. Isn't it supposed to be 95? 68, 90?
Yeah.
Yeah. I say 96. Huh. Interesting. Nobody stopped me.
I wrote it.
Like we changed the rule all of a sudden. What?
Oh, I didn't notice that. I just wrote down 95 on that paper.
Me too.
So that means at this college, that, 95, if it ever asks you to interpret this, it's saying that 95% of all their GPAs, all the freshman GPAs at that college, was 3.26 to 3.54. 99.7 were between 3.19 and 3.61. That's pretty high, isn't it?
Really
I was going to say. I mean,
Well, what about the people with 4 points? Or like,
they're way up here.
that's like so many standard deviations away.
Yeah.
That's rare.
It is rare, but in this school, it was rare to even have below a 3.0. That's
where I
rare.
got the fridge. Excuse me.
Okay, next question. We get to review something else you probably don't remember how to do. You have a museum, they have levels of membership based on how much they donate. So on the left, you have how much the people donate and then the percent that donate that amount. So 41% donate $50 and so on. Anyone remember what this whole little table's called? Yeah. Actually, it's called a probability model. It's been a long time. Plus it was probability, which you were very fond of. I know. Okay, and this whole thing is the population for that museum. Okay, so first it says find the mean and standard deviation of the donation. So it's saying the population mean and the population standard deviation. There is a way to do this on your calculator. Any guesses? Make a list. Make 2 lists. You see a table, you're probably going to make a list. Since this is percent, make sure you type them in as percent. So don't type in 41. Type in 0.41, 0.37, and so on. Sorry we're not using the random number generator today. One day only. Okay with that. Okay. Now, anyone remember how to find the mean and standard deviation? We're on the table. We're trying. You go to stats. Okay. Calc. Good. We're calculating some statistics. It's actually just one variable stat. But depending on how your calculator sets it up, the way mine is, I have to put L1, comma L2 after I hit variable stats. I don't guess it has to be in parentheses. And then some years it gives you a table. It says frequency, or it says list and then frequency. So the first thing would be L1 and the second thing would be L2. Hit enter. And what's the mean? Yeah, it's the very first thing. Notice what symbol does the calculator use for mean?
X or
Yeah, the calculator's dumb. It doesn't know that that's the whole population. They think it's a sample, but it's really the whole population. So just because the calculator uses its bar doesn't mean you do.
Why did I get 128?
I don't see.
Did you know 137 is my favorite food?
No, I didn't.
What,
It's a great number. That was your favorite.
137.
137.
Oh, I know it is.
And the standard deviation is 148.6. Are you confused? Anyone confused? It's okay to say you're confused. During the annual membership drive, says they hope to sign up 50 new members. So 50 is their sample size. It asks, how do you expect the sampling distribution model for any one day to look? So if we have 50 new members, what do you think it's going to be? Skewed, normal? Yeah, because it's larger than 30. Even though, can you tell by looking at this table, is the population, is this skewed left or skewed right or symmetric?
Right.
Skewed right? Because most of them are over here and there's only one person that donated $1,000. They put their name on the museum. So we expect it to look like the normal model with mean, right back. What's that? Random mark. What's the mean of our normal model going to be?
137.5.
137.5. And the standard deviation of our model?
148.56 over further.
Yeah, so 148.56 divided by rad. Got almost exactly 21.
Yeah.
So you're just using the formula, plugging in, find this mean and standard deviation. Okay, now the fun part. So some of you really need to pay attention because you didn't get this when we found probability. We did proportions. So it says one of the museum volunteers sets a goal of getting an average donation of at least 150 from the new members. Okay, so 150 is somewhere in between here. Is that a practical goal? Yes.
300 at least.
Okay, change yours to 150. Sorry, you're right. Your notes say 300, change it to 150. 300 was ridiculous. Okay. Does 150 seem like a reasonable goal?
Yeah.
Somewhat.
Somewhat, right? There's not too many that donate over 150. There's a bunch that are below 150. But to get an average, she might could do that. So we're going to find the probability, you know how to find the probability, that she gets an average, X bar, an average, of at least 150 per new member. At least, greater than or less than, greater than or equal to, which, okay, doesn't really matter. So now you get to think back. What do you do next? When you're doing probability. Right, so 150 minus,
137.
yeah, we just found the mean, 137.5 divided by 21. Exactly. So use the mean and standard deviation from the normal model. Okay, now what do you do to find the probability?
So does normal and the CDF.
Yes, so normal CDF negative infinity to 0.595 or 0.595 to infinity?
0.595 to 30.
Yeah, 0.595 to infinity because it's greater than. And the probability is about 28%. Pretty close.
Can you do the 0.595?
Yeah, 0.595 to infinity. Okay, so anytime it asks for probability and you have a normal model anywhere, you need to find the t-score in normal CDF.
How particular are they going to be on rounding?
Usually, for probability, if the word probability is in a problem, it's standard use 4 decimal points, or a percent in 2 decimal points, like 27.59 or 0.275.
I mean, like, whenever you...
But I rounded 0.595, which
Yeah,
would
like,
change it.
in all
That's
of
not a big
those-
deal. Anything else? Okay, we can go through the last problem a lot faster. Now that I think you have the idea, you remember everything. Okay, so it says a waiter has a distribution of tips with a mean of 960 per party and a standard deviation of 540. Any waiters, waitresses in here?
Heck yeah.
I was gonna say, is that a good average? 960 per table?
Yes.
Yeah.
Almost $10 a table. Okay, so that's this waiter's mean. Standard deviation of 540, which means a lot of times it's above that. Unless it's below.
That's pretty good.
What?
That's pretty good considering you're waiting like 6 tables an hour.
Mm-hmm.
So, yeah.
So again, it asks about probability. It says, what's the probability that his 10 parties today will find an average of no more than $10?
Less than.
Less than or equal to 10. Okay? You need to do the z-score, but here's where a lot of you are going to mess up if you're not careful. It seems easy just to use 960 and 540. But if I do that, there's one piece of information I haven't used at all.
Distribution of A.
Yeah, there's 10 parties. That's a sample size. That means it's a sampling distribution. Anytime you're given that, you have to find the mean and the standard deviation for that sample. Okay, so it's saying it's different. This is his whole population. So for as long as he's been a waiter, that's his average and standard deviation. Now we want to find his average and standard deviation when there's just 10 parties, like almost, I guess, per day or per hour.
Okay, so that would make those parameters instead of statistics. Those are statistics.
Yes.
Yeah.
What is this one? So 960, that stays the same. The new standard deviation,
1.707.
540 divided by radical 10.
Yeah.
So about 1.71. That's a 7. Don't worry. Well, I did round to 2 decimal places because it's money. You know, that's a pretty common way to round money. You round however you feel. 10 minus 9.6 divided by 1.71. About 0.23. And then normal CDF, negative infinity to 0.23 or 0.23 to infinity? Yes, negative infinity to 0.23. So, can he expect to average at least $10 per party? Yes. Either a good waiter or they just tend to tip well. Okay, can you do the next one on your own? Is that asking too much? It's asking too much. What? Okay, it says now he's waiting on 40 parties. Oh, there is something hard about this one. And then we want the probability he'll earn at least 450 in tips.
It says 400 on paper. Just change it.
Oh, what's it say on yours?
400.
Well, okay, we can do 400, that's fine.
Could we divide that 400 by 40?
Yeah, so that was going to be the first thing I was going to say. We're dealing with averages here. 400 is not an average. That's how much he expects to make total. So how much does he want to make on average? Yeah, 400 divided by 40 is $10 again. Probability he'll earn at least $10. Now, I'm glad we're using this number because I can ask a good question. So we're doing the same thing. Are we using 10 again? Is the standard or the z-score going to be the same?
No, the population says right.
Right. We just changed the mean. Well, we didn't change the mean. We changed the standard deviation. So now the standard deviation for that sample is 5.4 divided by radical 40. 0.85. Okay, now you try it. Find the z-score and see if you can find the probability. At 447 for the z-score. Here for the probability.
At 31.91.
Okay. 991 or 9?
I got 97.
But that might not.
Oh, okay. I guess it depends on how you run it. That's what I got. It depends on how you run the z-score or the standard deviation. That's close enough. I mean, it's all 32%. Okay, that's going to be the main thing you're going to do with sampling distributions, is find the probability. Anyone have questions? Nice, smart, intelligent questions. That would benefit everyone. Nobody? Ready to do the last one? It says, how much does the waiter earn on the best 10% of his weekends? So, this time we're given a percent. We have to work backwards.
What the z-score?
Yes, how do we find that? Please.
0.1 equals 10 equals.
Point 1 is not the z-score.
Oh, yeah, that's right.
Point 1 is kind of it's the area under this curve. You want to do backwards. Yes, you do the inverse norm. You do inverse norm of 0.9 or 0.1. It's 0.9. The inverse norm is always from everything to the left. So you do the inverse norm of 0.9. inverse from 0.9, because that's everything to the left, it's 0.28, so 1.28. This is the z-score. And then you just set up the equation and go backwards. 1.28, we're trying to find how much he averages on the best 10%. 9.6 is his mean. What are we going to use for the standard deviation?
Oh, wait, wouldn't it be
Point
the
eight four.
0.5?
Yeah, 0.85 because 40 parties, and that's the standard deviation when there's 40 parties. Now it's just algebra problem. 1.28 times 0.85 plus 9.6. Is that right? Someone gets-
That's what I got.
Yeah, so say on his best weekends, he averages $10.69 per party. Okay? And that's fine, you can write that as your answer. What if it said how much does he expect to earn total for on that weekend? He has 40 parties. And so that's an average. Yeah, just multiply by 40.
That's $400.
Yeah, so before 427 something.
10.
Oh, I rounded. Then we're done. 32.